Hi everyone, my name is Ayush. I'm a senior software engineer at WePay. Today I'll be talking about our near real-time reporting pipeline here at WePay. Additionally, I have Yuzu with me. She'll be presenting as well. Yuzu, you want to say quickly hello?
Hello, everyone. I'm Yuju.
Great. Let's get started. And I think Alex and Chris have done a great job of sort of setting the stage of sort of what these core technologies are. And now we can sort of dive into sort of a real world application of how we're actually using these technologies to sort of cross the chasm, like Alex was talking about, and sort of update our legacy reporting infrastructure. So the agenda, we'll sort of do a top down. We'll talk about what reporting is exactly from a product perspective. And then we'll sort of jump into how we, traditionally at WePay, we solved sort of the reporting, sort of the initial idea of what reporting was, and then how it evolved over time and sort of thinking it more as like a data product and how we're trying to create a real-time infrastructure using Pinot and Kafka. And we'll leave some time at the end for Q&A. So I want to start off by talking about like what exactly is reporting, and reporting can mean different contexts and different companies. WePay is a financial technology company. We are processing payments for merchants on platforms, right? The way I like to think about reporting, it's a collection of human readable or understandable data that provides some level of insight on lower level activities after it's happened, right? So think of it as a who, what, why, when, and where about a transaction or a merchant or a platform, any event, right? After it's occurred. It's not a fortune telling, future seeking type of thing. It's sort of after the fact, right? And we, on our layer as an infrastructure layer, we're really trying to be agnostic about the final form of the report. We want to let the data presentation handle that, right? And another important thing to keep in mind is that reporting is not responsible for the creation or deleting or modifying of data, right? Usually it's just data presentation. So we rely on our source tables or source teams to populate events correctly and verify that the business logic, it makes sense, right? So they're responsible, and we started reading that and providing APIs and infrastructure for people to access that data quickly and accurately. So, if you were thinking about what a report looks like, an idea might be, hey, it looks like just a CSV file and, a bunch of data about activity has occurred. And yeah, I mean, that's true. If you're working with financial reporting, a lot of financial reporting does look like that, right? And we do power and generate these type of reports. And the really challenging thing about this type of reports is you want the report to be scalable in both dimensions. And by that, I mean is you want to be able to add more columns to this CSV file. And that new column can come from a new data source or a new microservice or something. And you have to stitch that together into a canonical data representation or a CDR about what a transaction looks like or what a merchant activity looks like, right? And you also want to be scaling on the record, on the row level, in that a report can have 5 records on it, or it can have 5 million, right? And you still want to reliably send it to the end user who's requesting the data in whatever format they want. And hopefully the data presentation can show those 5 rows or 5 million rows accurately, right? But also reporting is also sort of what Alex was saying is dashboards, right? Here at WePay, we have a merchant-facing dashboards and we have partner-facing dashboards or platform-facing dashboards where people want to log in and see, hey, what are transactions that occurred? What are my KPIs? What are my metrics? How's my business doing? Think of if you're running if you're running a lemonade stand, right? You want to know how much lemonade I sold today, how much money am I making, how much I paid in fees, all these metrics and KPIs and all these transactions are showing up. And historically, we have been able to power this. We have built a sort of robust, legacy reporting infrastructure. And the way, quickly to follow the flow is there's 2 main pipelines. There's a data ingestion flow, and then there's a data retrieval flow. So the data, ingestion flow is we have a Apache Airflow trigger job that sends a request to BigQuery every 30 minutes. BigQuery, what we do is we stitch together all these source tables of historical data and even the new data that came in via the Kafka pipelines that Faraj was talking about that our data infrastructure team provides, right? And we stitch together all this data via a 500 line query, and we sort of join and do some data manipulation, and we combine all this data into these canonical data representation tables that are outputted, and these are updated every 30 minutes on a batch basis. But obviously, we want to allow people to synchronously retrieve that data, right? You can't reliably make a BigQuery query request in a synchronous API call and fetch it. And if you're trying to meet a sub 100 millisecond latency, it's not viable. So we have a whole microservice whose job is to basically, the Airflow job then says to the ingestion task manager, hey, these tables are now ready to be ingested. And now we are loading the data from these canonical data representation tables. We're ingesting it down into a MySQL database, right? And we can do, differential loading of the data, or we can do full loading of the data, depending on, how heavy it is to like the volume of data, depending on the canonical. So it can be a transaction model, which is a lot of updates are occurring. So you want to do a differential load there versus some type of activity about, a user's address being updated. That's not occurring often. The number of events occurring in a 30-minute period aren't often. So you can probably get away with a full reload there because you're not dealing with millions of lines of items. And you also have to keep in mind we're handling, 2 years of activity, right? People want to be able to access that volume of data. So it's not just a trivial thing. You really have to be really careful about data quality and how you're ingesting all these things, right? So you, after you have it from the ingestion task manager, we store it in the database. And then you basically have a very simple, we heavily use gRPC here at WePay that allows a reliable client and server interface for clients like our UI UX team or anyone to basically make a call and retrieve the information quickly, right? And we have the reason why we use gRPC specifically for reporting is we're able to have really good data models and really good contracts between our clients from our server side, and we can say they can expect the format and the style of the data. If it was a JSON payload, that contract wouldn't exist. So if something changes overnight, with gRPC protobuf, we're able to really say that, hey, a contract exists, it's sort of written in stone, and any future changes will have to be backwards compatible. And that's the guarantee you can get as a client for our server, right? So that's why we sort of created this sort of gRPC related data retrieval pathway, right? But obviously things change over time. So one of the main changing things is there's a changing product landscape, right? And one of the capabilities is we are, as a company, moving more into card present or terminals. If you're not familiar with card presents or terminals, every time you go into maybe an ice cream store or a small shop, it's those small little card readers that people can swipe your card in, you can tap it, you can dip it, and it processes payments. An example is over here, right? And we're also moving into really more complex billing reports that are really, trying to show a lot of information that's not as simple, like who, what, why, when, and where about a transaction. It's like really nitty-gritty fee information or really nitty-gritty onboarding or risk information, right? It's really much more complex reporting. But also another thing to keep in mind is the pandemic, right? The pandemic happened and a lot of small and medium businesses have moved their business online, right? And that means that they're processing payments online. So we're dealing with the higher volume of payments, right? But people also want a holistic product where they're not only processing payments online, but they're also doing their financial reporting and auditing and verification online. So you need to have a much more accurate and much more robust infrastructure from a reporting perspective to sort of meet customer needs. And oftentimes our customers are saying, we want custom reporting and we want custom metrics. And the legacy infrastructure that we have, we have a query that's sort of set in stone and we think this is the cookie cutter reporting that everyone wants. And it's really hard to modify that set in stone thing. So we, as you can see, we're sort of going into the idea of why we need Kafka, why we need Pinot to provide sort of that custom ability to make changes on the fly, right? Also, in general, people are becoming tech savvy, right? Everyone's using an app. Everyone expects things to be ready now. People are not okay with waiting 30 minutes for something to show up, right? And that's not, something that's viable in a card present world, right? If you're a small business owner and someone comes in and swipes a credit card on your terminal, right? It's not okay to say, hey, let's wait 30 minutes to see that transaction show up and all the state changes, right? They want to see that report and all those dashboards and all those metrics and KPIs update instantaneously, right? these are some of the issues with the legacy infrastructure, right? We're not able to really meet that 30-minute SLA. A lot of times in the legacy infrastructure, we're pre-calculating our KPIs and metrics, which are great, if you have cookie cutter metrics, but if you're trying to support custom in a synchronous flow, you can't do that with the pre-calculation. Adding any new features or functionality just came with the whole huge development overhead of really trying to test and verify all your query changes. You're trying to touch a behemoth of a query that sort of does all those joins. You're adding a new join in, and you're like, oh, am I breaking something, or is my query performance going wrong, or is BigQuery optimized for changing something too rapidly? So it just adds a much more timeline for getting a product or feature out of the door, right? And so we have this legacy infrastructure, and the user will sort of talk about the new real-time infrastructure. But one of the benefits that we're able to get of saying, let's ditch the legacy and sort of move on to this new real-time infrastructure is we're able to design with sort of a blank slate and sort of learn from our mistakes and figure out, okay, we need something that allows us to have flexible design that improves developer velocity when we're adding new features, right? We can still keep that strict data modeling and API contract with our gRPC protobufs, but we can make it better, right? We've learned from where we made mistakes in the past and we can improve on it. And we can also have a good separation of concerns between our data declaration layers and our raw data lake that sort of populates the data information, right? In the previous legacy infrastructure, we're sort of doing that all in one step. So every time you're making a change in the data declaration or data population, it requires you to get into the nitty gritty, right? If you're able to do that separation of concerns, you're able to sort of, if you're just making a simple data declaration change, it's a lot more easier to get that into production rather than coupling these two things together. And basically a high level overview of sort of what the new reporting pipeline and the real-time infrastructure is that at WePay, we have our data infrastructure team and DevOps team provides us a very robust, Kafka, Debezium, Apache Pinot, and MySQL setup, right? And we are consuming all these data feeds and all these technologies that are built in by our infrastructure teams, and we're using it in our new microservice, our data infrastructure microservice, right? That's sort of populating a near real-time canonical data model, right? That is being populated in a MySQL data store as well as in Pinot. And then we are exposing a gRPC sort of reporting gateway. If you're familiar with maybe domain-oriented, microservice architecture, it's a single entry point where people can you have a contract and sort of access everything at reporting, whether you're an internal user or an external user, you're able to get the reporting information out and establish a contract with their clients, right? So they know what to expect. And basically we do all the data modification and data declaration on the gateway layer. That way our data infrastructure microservice can just be focused on, getting the events, right, writing the events and putting them in a way that they're able to be read properly in a raw data format that can be transformed in whatever way on the gateway layer, depending on however the client needs it, depending on the client's use cases or their request, right? So it's much more robust, much more flexible. And yeah, here I'd like to hand it off to Yuzu, and she'll continue talking more in depth about the architecture of the data infrastructure microservice.
Sure. Thanks, Ayush. Hello, everyone. I'm Yuzu. I'm the last speaker. In this session, I would like to discuss why we need this new data infra service and how we leverage open source platform to design and implement it. So in this project, we would like to accomplish 3 major goals. One is building a CDR mechanism. CDR is also known as canonical data representation. And 2 is collecting data from external services through the entire company. 3 is providing data for some usages within our reporting team. Next one, please. Okay, move to the architecture. Before we start, I would like to quickly go through the dependencies of this service. As you can see, we have Kafka as distributed messaging system to transfer data. And we have Debezium as a Kafka connector between MySQL and Kafka. It works to capture data changes in MySQL. through the MySQL binary logs and publish data changes event to Kafka. Besides that, we have 3 DBs in this project. MySQL is used as a relational DB to run all relational joins. Pinode is used as a search DB to solve MySQL limitations. We can talk about these limitations later. And also Pinode consumes from Kafka topics and insert into Pinode tables in a stream, which perfectly matches our near real-time requirement. Also, we have BigQuery. This is mainly used for the reconciliation project, and it supports a good permission control to give visibility to our engineers to debug any data issues. Next one, please. Cool. Let's jump into the system design. The workflow starts from the external data sources to explain this data. For example, for our near real-time reporting data model, as Ayush mentioned, for each transaction, we need information of who is the sender, who is the recipient, how much is the transaction amount, and when does this transaction happen. Also, something about the credit card information or bank account information. This data generated by upstream microservices and published to Kafka cluster. Our data infra service consumes Kafka messages and directly insert or update data into corresponding MySQL tables. We call these tables as upstream table or source tables. These tables are maintained as a relational model and or the denormalized model in MySQL. Until now, we are able to collect all required external data and store them into the relational DB. Next one, please. Cool. Next step, we want to convert from a normalized data model to a denormalized data model. To someone who isn't familiar with the normalized data model, in short, a normalized data model has multiple tables and can be joined with their relationship. A denormalized data model combines multiple tables into one. In that case, the latter one can be queried quickly. So to achieve that, MySQL binary log, which is a global log containing all of the data change events, is monitored by Kafka connector, which is DBs in here. And then these events are published to Kafka. Next one, please. Now move to the red box, our infra service. Service consumes data change events of its source tables and regards them as a data change notification. These events triggers a read and write process, which means reading from the relational DB with joins and then write the query result into the downstream denormalized view. We also put this downstream view to Pinode to support a better performance. Next one, please. In the meanwhile, MySQL data will be also synced to BigQuery through the Kafka and the Kafka connectors. Also, our client are able to call gRPC API to query information from the downstream view. In conclusion, our service collects external data and insert into MySQL DB with a relational data model. And these source tables data changes are published to Kafka. And then our service consume data change events again and trigger a read and write process to build a denormalized view. Now, I believe some of you might have questions in your mind. Why do we publish and consume data twice to make our design so complicated? To help you understand why we design like this, let's step back a little bit and share the challenge that we have before making this decision. Cool. So in this picture, the left part is our previous design diagram. As you can see, we don't have the second round of producing and consuming process. Data infrastructure directly read MySQL binary log and put all data changes event into a global queue and write to the denormalized view in the synchronous way. So here comes a question. This data service is a distributed service. However, running multiple pods to process same bin log event causes conflict. Therefore, we have to keep only one pod running the read and write task while locking all of the other pods. This significantly reduced the throughput and caused the bottleneck. With the new design, which is on the right part, because one of the benefits of Kafka platform is supporting a high throughput. This problem can be perfectly solved by Kafka and the Kafka connectors. So in the new design, each MySQL table maps to one Kafka topic. Compared with previous design, we have two major improvements. For one pod, each table mapped to one corresponding Kafka topic instead of using a global queue to manage all the tables data changes event. For multiple pods, new design consistently processes messages from Kafka instead of just one pod processing all of the events. Until now, new design remove the throughput bottleneck and make our infrastructure horizontally scalable. Right, so that's how Kafka platform with Kafka connector helped us. Next one, please. Cool. So far, so good. Cool. Let's move further. Kafka also has some limitations. You know, nothing is perfect. Fortunately, our data infra service is able to manage these problems. Three traditional questions also considered in our design. One is Kafka doesn't guarantee 100% no data loss. Second, Kafka doesn't have idempotent logic. Third, Kafka doesn't keep message in sequence. So for the first question, the answer is pretty straightforward. In our system, the problem is handled by automatic data quality check. Once a data loss event is detected, we would like to run the data backfilling immediately. So for the second question, it's also general. So in our system, we keep the primary key for each table for the deduplication logic. After that, we can guarantee there is no duplicate data exists in our DB. But for the third question, this is a little bit complicated. Before we discuss the solution, I would like to give you some context of why we have to keep message in sequence. As we discussed earlier, we have two types of tables. One is relational source tables, and the other one is the denormalized view. We keep a relational data structure in a tree structure, like the example shown on the right side. The circles represent source tables, and connections represent join relationship. Each downstream view mapped to one entire tree, and each tree has only one root node. All of the child node can join back to its parent node by the relationship, and you know, the eventually the downstream view is able to have the combination of the data within the source tables. These view structures are maintained and managed in our config file. We can easily add a new denormalized data model without any data changes. So in the near future, we can even let customers to handle the new features adding by themselves. Cool. Coming back to the sequence problem. For the source table, for instance, we expect update events to follow with an insert events since update events are the data changes happened in the table for an existing record. But when changes happened very fast, like within 1 second, we can't make sure they are assigned into same Kafka topic partition. Likewise, insert events are not able to be guaranteed be received by server before the update event all the time. So this causes the data execution issue if we don't handle it. So come up with a solution. To solve this problem, we treat all of the update events as absurd, which means when we receive a update event, we try to execute insert first. If no records exist in the destination table, we know that we receive an update before the insert event. Record will be directly inserted into the table. But if a duplicate key is detected, we will compare the record modify time and the update related fields from the change data in the update event. Moving forward, for the downstream table, we keep the eventual consistency, which means for each row in the view, we don't expect all columns to have value when it is initialized. It's possible that some child node data got delayed while the new record is inserted into the downstream view. We just keep child information as none at the first time, and then once the upstream data node receive the data, they will backfill their correlated column values to the downstream view. And in that case, we can accomplish eventual consistency. That's how we manage the Kafka limitation and to accomplish near real-time denormalization. Cool. Besides Kafka, Pinot plays an important role in our project as well. In general, we use Pinot because of the MySQL limitations, as we mentioned earlier, and the product requirements. So we found that one major MySQL blocker is the maximum number of indices in the InnoDB. So that the number is 64. But as we talked, our downstream denormalized view is a combination of multiple tables, and customers read from these views. To give a better query performance, we have over 100 columns that require indexing in one denormalized view. Therefore, 64 is not enough to support our use cases. And then talking about the product requirement, we will support real-time KPI, which is querying the total amount of the transactions in the past 2 years for one merchant. Also, we have metric calculation and partial text searching. For example, merchants want to search their name by just typing first 3 letters. Based on this requirement, Pinot is a good choice. Here I listed some benefits of the Pinot. So some of this has been covered in the Alex's presentation. So the first benefit, pre-aggregation for some columns. So this feature can be used in Pinot real-time tables. There are 2 types of tables, real-time and offline tables. So pre-aggregation columns can be added into the config. Once the real-time data is consumed, the value of this column will be added into a separate row to compensate a pre-aggregation rows. And so for the second benefit is smart indexing, which is included in Alex's slides. Pinot has some brilliant algorithm to support different types of indexing. Like one we used is like sorted inverted index. For example, one of our use case is like merchant want to have their bank statement for the last 3 months. So in our transaction level view, we have a lot of records in the table with same merchant ID. And the merchant ID is the filter condition when this query is running. So the sorted indexes, inverted index ordered the transactions which have the same merchant ID together and keep the range of the row number as a dictionary, so that for each query we have a log n time as improvement. And also we have range index. This is similar as the last one. This is used for filtering over the range, like we need some value larger than or smaller than a certain number. Also, the text search support provides a better performance for string type. Last but not least, so we have a lot of use cases like frequently used query and the Pinot support some of the situation very fast. So for example, for running the same query and frequently use the query, Pinot will keep the record position into the memory to make subsequent calls faster. We also found this fact during the test for a table with 1 million rows. The second query call will get 25 times faster than the first one, which is great. Next one, please. So talking about the achievement, for now, we have accomplished a near real-time reporting, which decreased the data processing time from 30 minutes to 2 seconds to achieve the low latency requirements. And also we are able to serve 200K insert and update event per minute throughput in the CDR model. Also, this is no more traffic in our production environment. As we discussed earlier, our system is supporting the horizontally scalable now. And so if needed, we are able to serve 2 times or 3 times traffic without upper boundary. Next one, please. Cool. Finally, I want to give a big thanks to the team. Thanks Letian, Xiaoyang, Yue, and ASA's collaboration and hard work. Also, thanks for all the support from our manager, Sankit. And Q&A.
Great. Thanks, everyone.